So now we are going to the constraint optimization territory. Constraint optimization could be a lot more complicated than unconstrained optimization, in that we not only have objective functions, but we also have constraints we need to satisfy. So a general way of writing a constraint optimization is we want to minimize over the space of S an objective function of J. While I have some other constraints to satisfy. Maybe I have some equality constraints, right? CE of S has to be equal to 0. I also may have some inequality constraints. CI of E has to be greater than 0. Okay, so these are the kind of a general constraint optimization problems. So a key thing to consider, a very useful technique in constraint optimization is the concept of Lagrange multipliers. So the idea is the following. If I have a constraint optimization like this, I can construct a Lagrangian. And the Lagrangian is the J of S plus a certain Lagrange multiplier, let's say lambda E times CE of S plus another Lagrange multiplier lambda I times CI of S. If I'm minimizing the objective function and I'm satisfying these constraints, then both of these terms I'm adding should be what? Oh, let's actually consider the equality constraint case first. So let's actually consider, first of all, this case when I have objective function and an equality constraint. It's easier to see that if I'm adding a Lagrange multiplier, so lambda is called the Lagrange multiplier. Then the term I'm adding actually has to be exactly 0, right, at the solution to this optimization problem. So if I'm minimizing this function, I might as well be minimizing this entire function. But do I always, so the question is, can I obtain a specific value of the lambda E such that if I'm solving the constraint minimization problem, then I'm also solving the new optimization problem with the Lagrange multiplier and vice versa? How can I know that? I need to know the gradient of CE of S. Why is that the case?
Because if CE of S was something a lot less than 0, very close to the minimum of J of S, then that could like move the minimum of the combined function.
Right, actually that's the case. And let me actually formulate your words a little bit more graphically. All right. So let's imagine it's again very easy, a lot easier to think about a two-dimensional case when you have two parameters. And again, think about the contours. Now think about the contours of J first. So let's use red to denote the contours of J. If I don't have any constraints, the minimum of J would be at the center of these contours, right? Now imagine I have a constraint, and let's use blue to denote the constraint. And again, the constraint function can also be represented as contours, right? So the contour of the constraint function may be like that. All right. And there is, because my constraint is the value of the constraint function has to be 0. So there is a particular significance on the constraint where on the contour where CS is equal to 0, right? Maybe this one is CS equal to -1, this one is CS equal to 1, but this one has a particular significance because on that line, the constraint is satisfied. Right, does it make sense? So if I have a three-dimensional space, then that contour wouldn't be a line anymore, it'll be a surface, right? And again, if I have a 3-dimension but 2 constraints, then again it becomes a line. So let's think about, in this case, how do I solve this constraint minimization problem? Along this contour of CS equal to 0, where do you think is the minimum of the red objective function? Yeah?
A point that minimizes the difference between the minimum and the straight line distance between the minimum and the...
Okay, so your idea is at the point where the red and blue lines are of the minimum distance?
Yeah.
So what's your
I was going to say it's when the normal vector to the those like contour lines is pointed towards the optimal value. Just like the problem with the closest point to the origin, like the one some like surface out here.
It's saying like it's the point where the blue line is closest to the origin?
Well, yeah, but it's the point at which the normal vector to the blue line
The normal
pointed directly at the optimal for the red.
They're saying the normal line of the blue is pointing directly towards here.
I think that makes more sense than this.
I think they're equivalent.
Because
Then you have to know where the minimum is first to do that.
Yeah, you have to know where the minimum first is to do that. And so, first of all, both of you are right in some aspects, but like we are still a little bit away from the exact right answer. Just keep thinking. Yes.
Where the gradient of CS is parallel to the gradient of J.
When the gradient of CS is parallel to the gradient of J, you got the right answer. How did you get that?
Because that's like just where the blue line is grazing the contour of the minimum possible red line on the blue.
Right, so the gradients are parallel, meaning that the contour lines, they are tangent.